Okay, now consider a corollary of the theorem. So suppose we have a function that is integrable over the interval ab, then we can show that the limit of this as h goes to 0, as h goes to 0 is equal to 0 for almost every x. So for almost every x, fixed x, and take the this kind of average of this integrand over the interval 0 to h, this gets the limit is going to be 0 as h goes to 0. Okay, so the proof is pretty simple. So before we prove this, let's show what's the connection between this one and the one we showed before the previous theorem. We showed that, say, if we define f of h, f sub h of x as a function of x is equal to that, say x plus h f of t dt. You know that this can be written as from the integral from 0 to h or x plus t dt, just a simple change of variable. Okay, and previously what we showed is that this goes to f as actually we showed is that this minus f of x is going to 0 for almost every x. Okay, so if we put this in, we'll get this is just the integral for 0 to h f of x plus t, the 1 over h. That's for the first term, and then minus f of x, right? But this f of x is independent of h, independent of t. So we can rewrite this as, this term can be written as 1 over h, 0 to h, f of x dt, because it's just this is f of x, just like a constant. So we can combine the two, we'll get that. So previously we showed that this is going to be the limit of this goes to 0 as h goes to 0. But here we're going to show a stronger one. We're actually taking the absolute value of the integrand, and we can still show that it's equal to 0 almost everywhere. Okay, so that's our purpose right here. Okay, the proof can be, I showed the proof, a pretty long one in the notes, but there is actually a shortcut to prove this. So for example, let's define this g is a function of h and x, and is defined to be the average of that, the limit that we're trying to take. Okay, and as you can see, what we're trying to show here is just to show that the limit as h goes to 0, we want to show that this is equal to 0 for almost every x. That's what we want to show. Okay, and apparently this is going to be greater than equal to 0. So if we can show that the integral of this g, if we can show that the integral of the g, or I should say, if we can show that the integral of the limit of g hx equals to 0, if we can show that this is equal to 0, then we know that this one, since it's greater than or equal to 0, and the integral is equal to 0, that means this integrand is equal to 0 almost everywhere, right? So we just need to show that the integrand, we just need to show that this integral is equal to 0. Then, since the limit here is non-negative, we can claim that the g of hx goes to 0 as h goes to 0 for almost every x. Right? That's what we can do. Okay, so to do that, we can just recall the Vattel's lemma. We show that on the one hand, the limit of GHX as h goes to 0, the integral of this is less than or equal to the lim inf of h goes to 0, AB GHX. So this is the integration for x. Okay, and on this side, we know that this is greater than or equal to 0. On the other hand, we know that the limit of this actually exists. This is what we proved in the previous theorem. I think the theorem above the two theorem above this. So recall that we just used the tonality theorem to show that this quantity here is just equal to the AB in the 1/2 h 0 to h f of x plus t minus f of x dt dx, right? And then we said we can exchange the order of this integral, and then due to the continuity of integration, we show that this actually goes to 0 as h goes to 0. So actually the limit here exists. So the limit here can be just the limit, not instead of the lower limit. And we know that this is equal to 0. And this shows that the limit GHX as h goes to 0 is equal to 0 for almost every x. Okay, and that finishes the proof. Okay, so so what this corollary tells us is that as long as the function is integrable, we can see that when we take the integral or take the average of the integral for this integrand, as long as h is small enough, this is just going to be arbitrarily small, right? Arbitrarily small. So this actually also tells us the following property. We say that a point satisfies this equal to 0, a Lebesgue point. So we say x a Lebesgue point of f if the limit we showed above as h goes to 0 is equal to 0. Okay, and what we show here is that almost every, since this is equal to 0 for almost every x, so we know that if f is integrable, then for almost every x over the interval, the f is the interior point, it's a Lebesgue point. So almost every, so the Lebesgue points are almost everywhere over the interval. If f is integrable, then its Lebesgue points are almost everywhere. Okay, so that's simply what it says. All right, so let's look at an example that can apply the result above. So suppose we have a function that is integrable over R, and for the interval AB, if the limit h goes to 0, the limit of this quantity is 0, then there exists a constant such that the function is just equal to this constant almost everywhere. Okay, so note that this is much stronger than before. It says that we shifted the function by h, and then we take the integral of the difference over the whole interval. Okay, not just from 0 to h, but the whole interval, and then divided by h. If this limit still goes to 0, as h goes to 0, then we can claim that function is a constant almost everywhere. Okay, so by applying the corollary above, we know that since f is integrable, we know that f has the bigger points almost everywhere. Over this interval. Okay, and what is claim? Well, from this, what we can claim is that, say, if I have two Lebesgue points, and let's assume that x1 is less than x2. Okay, two distinct Lebesgue points, and we want to show that the function takes the same value at these 2 points. Okay, we want to show that. And to show this, let's think about the integral of f of x plus t minus f of x. Let's look at this. Dx, take the absolute value outside. We know that this is going to be less than or equal to taking the absolute value of the integral instead. Right? And apparently, take the integral over the interval x1 to x2 will be less than or equal to the integral over ab, because the integral is non-negative. And what we can show that we know that this goes to 0 as h goes to 0. Right? That's what we know about this integral on the one hand. But on the other hand, we know let's recompute this integral in a different way. Okay, let's just split these two terms. The first term is x1, x2, f of x plus t dt. The second term is dx. Oh, I'm sorry, that should be h here. It would be OH plus h plus h. There is also h here. Then we have that's the first term. Second term is just the integral of fx dx. All right, so now let's look at the first one. We can do a change of variable. We can see that here the whole thing, I can call it y, for example. Then when x is from x1 to x2, the y is from x1 plus h to x2 plus h. x1 plus h to x2 plus h of f of y dy minus 1 over h, x1 to x2, f of x dx. Okay, so apparently I can replace y by x because it's just a symbol. Let's just use f of x dx instead. And then you can see that the first integral is from x1, so this is x1, this is x2, and this is x1 plus h, x2 plus h. So the first one, the first integral here is just this, just the area here. Okay, and the second integral here, or just the integral here, is the area here. So the difference of these two will be just the area here minus the area here. Okay, so that's the idea. So we can rewrite this as 1 over h, and this area from x2 to x2 plus h f of x dx minus, they all have this common factor, so I just always keep it. It's x1 to x1 plus h f of x dx. Okay, so remember that this is like the f h of x2. This is like the f of hx1. Okay, and we know that as h goes to 0, this goes to f of x2 minus f of x1. Okay, so on the one hand, we know that this integral goes to 0. On the other hand, we know that the integral goes to this. So that means this thing is just equal to 0. Okay, so the f of x2 minus f of x1 is equal to 0, which implies that f of x1 is equal to f of x2. So that means all the Lebesgue points have the same value, but the Lebesgue points are almost everywhere for this function. So that means the function takes this value almost everywhere. Okay, this takes this constant value almost everywhere. Okay, that completes the proof. Okay, now let's look at the more examples. Here I have a function f that is integrable. Okay. And then let's consider this fx, which is the integral of x of f from a to t, from a to x. Then we can claim that this f must be BV. Let's add bounded variation, and also the TV of f. Since it has a bounded variation, the TV is finite. This also the TV is bounded by that. Okay. Right. So to show that function f is bound as a BV, we just need to show that every we can just show that every variation of this capital F is bounded by this quantity. If you can show that, then the TV is bounded by that quantity as well, right? Because the TV is the supremum of the variation of this thing. Okay. So now let's say for any variation, for any partition, delta, which partition is a partition of the interval AB. Okay, now we can consider variation of f over the AB using this partition. We know that by definition, this is just a sum for I from 1 to n, f of xi minus f of xi minus 1, right? That's what we need to show. And apparently inside the integron, sorry, f, we should use the capital F, capital F. Okay, so according to the definition of the capital F, we know that is just keep everything outside. And the inside integral, this is just the xi minus 1 to xi, f of t dt. Okay, and apparently we can move the absolute value into the integrand. T dt. Okay, and this is just, sorry, just I from 1 to n, 1 to infinity. Okay, and this is just the, partition the interval and do this integration on each piece, and this is just equal to the integral over here. Okay, and now we show that for any partition, the variation will be less than or equal to that. And taking the supremum of both sides, it will be still less than or equal to the right hand side. And that supremum is the TV. So the TV of f is equal to the supremum over all the partitions of V variation of f. A, B, delta will be still less than or equal to this. Okay, and that completes the proof. Okay. All right. So so in the last subsection, we're going to provide a more complete theory about the relation between integration and differentiation. Remember that our ultimate goal is to show the fundamental theorem calculus exists or is true. So to remember the fundamental theorem calculates that for any f of x, we want to show that it's equal to f of a plus the integral of this derivative of f. Right? That's what we are trying to show. We want to show that in which case the function f is differentiable, and the value of this function is equal to fa plus the integral of its derivative. Okay, this is what we want to show. So previously, what we know is that the function, in which case the function will be differentiable, but a function is differentiable, not necessarily means that this holds. Right? It doesn't mean that it holds. So here we're going to provide a sufficient necessary condition for this to hold. Okay, and the concept is called the absolute continuity of function. We're eventually going to show that such fundamental theorem calculus holds in the Lebesgue case is true if and only if the function f is absolutely continuous. So to show what that definition is, so later. Okay, so first let's show a lemma. Okay, the lemma. Suppose we have a function f, and the derivative of f exists and is equal to 0 almost everywhere on this interval. Okay. Suppose that the function is not a constant. Almost everywhere. It's not constant almost everywhere. Then there exists just suppose that it's not constant. Then there exists epsilon 0 such that for any delta greater than 0, there exists a finite number of mutually disjoint sets, mutually disjoint intervals. We call them, say, x1, y1, all the way to xn, let's say xn, yn, such that the f of x or y, yi minus f of xi, for I from 1 to, we use p here, p for I from 1 to p is greater than or equal to epsilon 0. Okay, so let me repeat. It says that if a function is defined over the interval ab, and the derivative exists, then it's equal to 0 almost everywhere. Suppose that f is not constant. Say, well, this is 0 almost everywhere, and we know that it could happen that the function f is doesn't take a constant value. But if f is not constant, then there must be some epsilon 0, such that no matter how small the delta is, there exists mutually disjoint intervals like x1, so x1, y1, x2, y2, up to xp, yp, such that the sum of this absolute value of differences evaluate that the endpoints of these intervals is greater than or equal to epsilon 0. Okay, so that's the lemma. Let's prove. Okay, suppose that C is between A and B, such that the f of A is different from f of C. Okay, because it's not constant, so that means at least you can take at least 2 different values for some point at for some point C. So if this since we have this, then we can choose the epsilon 0 to be any number between 0 and half of fc minus fa absolute value. Okay, because these two are different, so this difference must be positive, so we can choose some epsilon in between. And then also choose r to be any number between 0 and the epsilon 0 over b minus a. Okay, just choose these two numbers. They are both possible. Then we define the set EC to be the set of points in the interval a to c where the function f has the derivative equal to 0 there. Okay, so just a collection of points where the function has derivative and is equal to 0. Then we define the family of functions, which will be a Vitali covering of this EC. It is defined as all the intervals like that. Interval AC. The f of x plus h minus f of x is less than r times h for some h. Okay, so if the point, if the interval x to x plus h satisfies this inequality for some h, then we can put it into this collection of sets, and then this f is going to be a Vitali cover of this EC. Okay, so the recall the Vitali cover of a set means that for any point and any epsilon, there exists some closed interval. So the Vitali is just a collection of closed intervals. So for any x in here and any epsilon, there exists some closed interval in f such that, so this interval called I, such that the length of this is less than epsilon. At the same time, x is in this I, where this x is from the E. Okay, so that's called a Vitali cover. And why this f is a Vitali cover of the EC is because the EC contains all the points whose derivative is equal to 0. So since r is greater than 0, we know that for h is small enough, we know that the f of x plus h minus f of x over h will be smaller than r, because the limit, we know that the limit, so for x in EC, we know that the limit as h goes to 0 is equal to 0, right? And that means for h is small enough, we know that this will be smaller than r, okay, for some h. And that means the x plus h, x to x plus h will satisfy that for some h. Okay, So actually every point is in here. Every point from EC is in the can be covered by an interval in the in F. Okay, and it doesn't matter how small it is. You can just always put H can be arbitrarily small, since this will hold for any H sufficiently small, right? That's why this is a Vitali cover of EC. And a property of the Vitali cover lemma says that for any delta, there exists a finite number of disjoint intervals from this Vitali cover, such that let me just write it down, be easier. By the Vitali cover lemma, we know that for any delta, there exists mutually disjoint intervals. We call this xi plus hi for I from 1 to say p, such that they're from F. Such that the measure of E minus the union of these intervals has a measure less than delta. Okay, or EC. Well, first of all, the EC, we know that the function f has a derivative equal to 0 almost everywhere. So that means this EC is almost filling in the interval AC, because over here, such point is almost everywhere. So EC is almost everywhere in A to C. So that means that this one has a this one has a measure C minus A, delta C minus A. And these are all disjoint, and they're all in this interval. So actually, this just can be this left-hand side is just nothing but the C minus A minus the sum of HIs as from 1 to P. Okay, so that's what the left-hand side actually is. Okay, we just know that this is less than delta. Okay, so now let's say we choose the delta to be we decide what the delta is later. Let's first keep this in mind, and then we will consider. Let's just draw the picture, maybe easier. Okay, so this is A, this is B, and know that I have this x1 plus h1, then x2 plus h2, all the way to the last one, which is xp plus hp, also xxp here. Okay, so what we know so far is that the intervals, the sum of the interval, will almost fill up the sum of this interval, this to here, this total length of what I drawed almost fill up the EC, and what's left is just the delta. Or it doesn't matter how small the delta is. And then let's call that this is a, say this is a U0, this is V0. And then we call this is a V1, this is a U1, all the way to the last one, which is the VP, UP. Okay, so this is what are the interval here. So the V0 to U0 will be just this over here. V1 will be just here. VP, UP will be here. Okay, and x1 plus h will be just this way over here. Okay. Now let's look at the length. So the sum of this ui minus vi for I from 0 to p, we know that this is just the sum of this length, and then we know that this is less than delta, right? It is less than delta. Since whatever left is this is just this part will be EC minus the length of this will be equal to the length of EC minus the rest. Okay, since the EC is fills up the entire AB or AC. Let's just see C here. Okay, just up to C. Okay, so now let's consider the FC minus FA. Okay, now I have FA, I have A and C, then this sum can be written as the, using triangle inequality, can be written as the interval, the sum of these things, xi plus hi minus f of xi for I from 1 to p, plus sum of the f of ui minus f of vi, where I is from 0 to p. Okay, so I know that. And then let's look at the first term. We know for the first term, we know that the xi plus h was chosen such that this one is less than r times hi. Right? So we know that. That's how we chose this Vitali cover. So with the xi plus h, either from the Vitali cover F here, and they satisfy this. So that means this is less than equal to the sum of r hi, I is from 1 to p, plus the rest, shall keep it here. All right, and then I know that the sum of hi's is this. Okay, they satisfy this. This is less than delta. Okay, and that means the this one, the sum of hi itself must be greater than equal to 0. So that's why this is less than equal to the sum, or it's just r times the sum of hi's, but the sum of hi's will be less than equal to c minus a. So this is just less than equal to r times c minus a. Right? So you keep this. Okay, and on the one hand, I know that this is less than equal to, since the way we chose this r is between 0 and epsilon over b minus a. So this will be less than equal to epsilon 0 over b minus a times c minus a. But this is definitely still less than epsilon 0, since c minus a will be less than equal to b minus a. Okay, we'll be adding the same term. Let me just move this. Copy it here. Same thing, just copy it here. Okay, so that's what we know. And on the other hand, we know that the epsilon 0 was chosen to be between this. So that means this is going to be bigger than 2 epsilon 0. So that's why this is bigger than 2 epsilon 0. Okay, now we can see that the sum of f of ui minus f of vi as from 1 to p, it's actually bigger than epsilon 0. All right, so so far we showed that for any epsilon, for some epsilon between this interval, which is positive, so this is positive, we know that there exists a set of intervals which are permanently disjoint since they are separated by these disjoint intervals xi to xi plus h. So these intervals are all disjoint, separated by those intervals, and the sum of them will be less than delta. For any delta, we can choose we can find that these are less than delta, and finally we show that this sum of these differences is actually greater than epsilon 0. Okay? For any epsilon 0, we found some delta such that this sum of these lengths are less than delta, and these lengths are disjoint, and eventually the sum of this is still greater than epsilon 0. Right? So that completes the proof. Okay, so this lemma is just to show that what will happen if we do have a function that is differentiable and the derivative is equal to 0 almost everywhere, but still can still get a non-constant function, and this characterizes what could be happening. If this weird situation happens, then we must be able to do this. Okay, or there exists evidence so that we can do this. Okay, so this is where the complication could come from. And to eliminate such issue, we can define a strong condition called the absolute continuity, and this will prevent that to happen. And the definition is just to try to counter that weird situation. So let's define the absolute continuity. So the function f is absolutely continuous if, so previously we showed that there exists epsilon 0 so that for any delta blah blah blah, then we can just replace that by do the reverse. For any epsilon there exists a delta greater than 0 such that for any mutually disjoint sets, mutually disjoint intervals x xi, yi, to use that open interval will be fine because the measure doesn't change. So xi, yi, I is from 1 to p. It doesn't matter how large the p is as long as it's finite. So for any disjoint intervals like this, satisfying the sum of yi minus xi is from 1 to p is less than the delta, there is the sum of f of yi minus f of xi as from 1 to p is less than epsilon. Okay, so this is the definition for absolute continuity. Okay, let's just try to counter the situation above. And if a function satisfies this, we call it absolutely continuous. And this actually will be shown to be the sufficient necessary condition for the f to have a derivative, and the integral of the derivative is equal to the f here itself. And that is the fundamental theorem of calculus we wanted. Okay, so we're going to reach there soon, but before that, let's give several simple results for the absolute continuity. So first one is that a function is absolute continuous means that it's continuous. Okay, and that's apparently true because for any epsilon there exists delta, then we can just choose the interval to be x to x plus delta, for example, and then we can show that the difference is less than epsilon. And for any h less than delta, f of x plus h minus f of x will be less than epsilon for any h less than delta. So this is just continuity of f at point x. And actually from here we can also show that this is not just absolute continuous, it's actually uniformly continuous, right? So the absolute continuous is pretty strong. It implies the function is continuous and also uniformly continuous. The second one is that the set of absolute continuous functions over the interval is a linear space. And to show that, we just need to show that for any constant a and b, and for any functions f and g in, that are absolute continuous, this is also in AC. Okay, and that's pretty easy to show. Just use the triangle inequality, and that would be pretty easy to show. So I will not prove this one. Let's see example. We said absolute continuity is pretty strong, but even stronger continuity is a Lipschitz continuity. Okay? That is something you are more familiar with. And what we're trying to claim is that if f is Lipschitz continuity, if Lipschitz continuous, then the f is AC. Okay, and let's say they're all on AB. Okay, the proof is super simple. It's just recall that a Lipschitz continuous function means that for any x, there exists some m such that the f of y minus f of x will be less than m times y minus x for any xy. Okay, that's the definition for Lipschitz continuous functions. Well, keep this in mind. We know that for any epsilon greater than 0, we can choose delta to be equal to, say, epsilon over m. Then, for any intervals xi, yi, where I is from 1 to p, and the sum of yi minus xi, we don't have to take an absolute value because y is always bigger than xi. Right? This is less than delta implies that the f of yi minus f of xi, we want to show that this is less than the sum of this is less than epsilon. But because the function is Lipschitz, so that means that each one of this is less than m times y minus xi. Okay, so it will be m times yi minus xi. Okay, and so that's why this will be just less than or equal to m times b minus a, because the sum of this will be that. Sorry, this times delta, because the sum of those intervals is less than delta. This will be less than m times delta, but delta was set to be epsilon over m, so this is equal to m times epsilon over m, and that's just equal to epsilon. Okay, so we showed that for any epsilon, there exists a delta chosen this way, such that for any disjoint intervals like that, with total length less than delta, we show that the sum is less than delta, and that implies the function is also absolutely continuous. Okay. Now I think we almost finished the preparation for the major results we have. So actually we have a series of results. The first one is that if f is integrable, Lebesgue integrable, then we define capital F to be the integral of this is in AC, is absolutely continuous. That means the integral of an integrable function, or say the f is integrable, then we take the indefinite integral. We got this function, then this function must be absolutely continuous. Okay, so this is in contrast to Riemann integrals. We already consider the function f that is differentiable. Where the f is differentiable, then we said this capital F will be different. Sorry, this f is continuous, then this capital F is differentiable, and the derivative of this capital F is equal to let f. But now we only need f to be integrable. It doesn't have to be continuous. And then we can still show the fundamental theorem. We'll calculate this one later. Okay, so to prove this, we just need to show that the f is actually, yeah, we need to show we need to recall the definition for absolute continuity and show that this capital F satisfies that. So first of all, we know that the lit f is integrable, so it has the continuity property. That means the f is integrable. We know that for any epsilon greater than 0, there exists delta such that for any say E is a subset of AB with the measure of E less than delta implies that the integral of f over E is less than epsilon. Right? That's the property about continuity of functions. That's something we know. And using this fact, see that for any epsilon and any disjoint set, that this will be the same epsilon above. So let this xi, yi is from 1 to p be disjoint, and the sum of yi minus xi is less than delta, then we can show that we need to show that the f of yi minus f of xi, this sum is less than epsilon, right? But now notice that this sum is going to be similar as before. It's just going to be the integral of xi to yi for f t dt. And do that for t dt. And this is less than or equal to the sum of the integral of the absolute value of the integrand. Okay, and we know that the sum of these intervals, so this is just nothing but just the integral, the union of these such intervals, right? The union of xi to yi from 1 to p of ft dt. But this one has a measure less than delta, so this means this is less than epsilon. Right? This completes the proof since we have showed that this will be less than epsilon as long as the sum of these intervals is less than delta. Okay, so this is one side, like when we know the function f is integrable, then we define this kind of function that is taking the integral of f up to x. This function will be absolutely continuous. Okay. Now let's see the next result. If f is absolutely continuous, then f is BV as well. Okay, so actually you can imagine that those will be pretty weak. We are getting pretty weak result because the function of boundary variation can be really can be a broad range. It's much more complicated than being just absolute continuous. But the purpose here is to show that the f, if it's in BV, we know that it can be decomposed as the difference of two monotone functions, right? That's what we're going to use, and because each monotone function is differentiable almost everywhere, and that's the purpose we're going to give this result. Okay, so to show that the function is also in BV, we need to show that the total variation is bounded, right? And to show that, let's recall that let epsilon to be equal to 1. Then we know that there exists delta such that if you have mutually disjoint intervals xi to yi for I from 1 to p, then the sum of this f of yi plus f of xi as from 1 to p will be less than 1, which is epsilon, if the sum of those yi plus xi is less than delta. Okay, and this yxi just destroyed. Well, we can just choose one interval, and if the single interval has a length less than delta, then we don't have this right here. We just say we have y minus x is less than delta, then f of y minus f of x will be less than 1. Okay, we don't have to have p of them. And that's also the case we're going to have below. So we can consider the partition delta, which is the partition of the interval AB with that xi minus 1 is less than delta. Okay, so if this one is less than delta, we know that the f of xi minus f of xi minus 1 has the absolute value less than 1. And we know that the total variation of f over this interval psi minus 1 will be less than equal to 1. The reason is that if we have this xi minus 1 and xi, and we know the length is less than delta, so it doesn't matter how we make this partition, the variation of f using this partition is going to be less than equal to 1, since the total length here is bounded about by xi minus x minus 1, which is less than delta. So the variation will be bounded by 1. So you take the supreme of the variation, we'll get total variation, but total variation will be also less than equal to 1 for any I. Okay, and that also means that the variation of f over the entire interval AB, we know that this will be just the total variation of f on each piece. This is a property of total variation on each piece. Sorry, it's I minus 1 to I minus 1 to I. It will be, each one of them is less than or equal to 1. So this is less than or equal to, let's say it's 1 to n. It's less than or equal to n. Okay, it's just equal to the number of partitions you have. But the point is not difficult since you have a partition and just make sure that each one of them has a length less than delta. Then there must be finite many of them, finite many of segments. And let's n be the number of segments. Then we can show that on each segment, the total variation is bounded by 1. Then the total variation of f over the entire interval will be bounded by the sum of this, which is bounded by n. And this is a finite number, and that means f is of bounded variation. Okay, and the corollary is what we wanted, since f is absolute continuous, then it is also of bounded variation, and then it can be written as difference of two monotone functions, monotone increasing functions, and each of these two functions is differentiable almost everywhere, so the difference of them is also differentiable almost everywhere. And that is a property of the space of bounded variation, right? So we just put all the properties of functions with boundary variation to this f. It's differentiable almost everywhere. The f prime is actually integrable. Okay, so that's just a property for the set of for the space of boundary variation. Now we're ready to show the final result, the fundamental theorem of calculus. So we just need to show one direction now because the other direction has been showed above. Let's say we show this. Suppose we have a function that is absolutely continuous, then as we know that f will be differentiable almost everywhere, and the derivative f prime will is integrable, and that's what we know from the previous corollary above. And then we can also claim that the f of x just equal to f of a plus the indefinite integral prime t dt. Okay, and we know that's true for almost everywhere, for almost every x over the interval ab. Okay, so here's the proof. The proof won't be difficult now, since we have all the preparations above. Because f is in AC, absolutely continuous, and then from the previous corollary, we know that the f is differentiable, and f prime is integrable. So everything on the right hand side is actually well defined. Okay, and also let gx to be the integral from a to x f of prime of t dt. Okay, just be the integral of this integrable function f prime. Then because it's an integrable function and we're taking the indefinite integral, then recall the result here. Here. So this is like f prime, which is integrable, and then we have this gx. So that means gx is in AC. Then g is absolute continuous. Okay, and since f is also absolute continuous, we know that f minus g is absolute continuous. So f minus g is also absolutely continuous, since the set of absolute continuous functions form a linear space. Okay, f minus g is absolute continuous. And also, let's check the f prime minus we know that the f minus g prime is equal to f prime minus g prime, and the f prime is just because of the f prime is the derivative of f, as we know, and g prime. The key of the g prime is that g equals to that. So the g prime will be equal to f prime almost everywhere, right? So that's because of g is defined in this way. So the g prime is equal to f prime almost everywhere. And so that's why this difference of these two will be just equal to 0 almost everywhere. Okay? And it's all equal to 0 almost everywhere. Then we'll claim that the f minus g is constant. The reason is if it's not constant, well, if f minus g prime is not constant, then recall the lemma we had. If f minus g is, so this is like f minus g prime. If the derivative is equal to 0, but f minus g is not constant, then we know that f minus g will have this property, which means f minus g is not in AC. But that is a contradiction to the fact that they are in, the difference is indeed in AC. So by the lemma at the beginning of this section, we know that the f minus g must be equal to constant. Okay, So this will be fx minus gx will be constant for all the x. And let's take a specific value x equals to a, then we'll have f of a equals to minus g of a equals to c. But g of a, according to our definition of g of a is just a 0. So this is just 0. So that means c equals to f of a. Okay? And that also means that the f of x minus gx equals to f of a for any x. And now we just put back the definition of gx. That means f of x equals to f of a plus gx, but gx is equal to the integral of this. Okay? And so we have that for almost every, for all the x. For all the x. Okay, so that's finished the proof. So now we know that the function f is in AC is the sufficient necessary condition for the derivative, for the fundamental theorem of calculus to hold. So if and only if there exists some function g, which is called derivative of f, that is integrable, and the f of x is just equal to f of a plus a to x g t dt. And in this case, actually g is equal to f prime almost everywhere. Okay, so that's the key result we obtained in this subsection. We want to see which case that the fundamental theorem of calculus is true. It is only if and only if the f is absolutely continuous. Okay, so from left to right, this is the fundamental theorem we just proved, and from right to left, that is a earlier theorem which shows that if we have an integrable function here, then the indefinite integral will be in AC. So that's the a result we showed slightly earlier. Okay, just a little bit earlier. Okay, so that's the main results. Let's see some examples. So suppose we have a function gk, which are all AC. Okay, suppose we have such kind of functions, which are all AC. And suppose that the gk at C, the infinite sum, converges. So that means this is a finite value. That's one thing. The other thing is that since that gk is in AC, so the derivative exists, and let's say that the sum of this is finite. So we have two properties. One property is that the gk at C is summable at one point C. The other thing is that these integrals from A to B, they are finite. And suppose these two are true, then we can claim that the sum of gk x exists for every x. For any x. And then also if we, since it exists for any x, we can define the g to be the sum, gx to be the sum. This is well defined. Just gx to be the sum You know that since this exists for any x, this is well defined, then this g is actually also in AC, and the derivative of g is actually the sum of the derivatives of k. Okay, so these two are also hold. Okay, so now let's recall what we have. We know that for the gk is absolute continuous for every k, and for some point c, this sum is just the sum of numbers, so it's a series of numbers and they converge. And also the sum of the integrals here is finite. Okay, the sum of this infinite sum of these integrals is also finite. And then we can show that the sum of the gk exists for every x. And let's define the infinite sum here to be gx. Then this g is absolute continuous, and also the derivative of g is equal to the sum of the derivatives. Okay, so let's see how to prove this. Okay, let's see how to prove this. So on the one hand, we know that since this sum gk prime x dx, since we know that this is finite, so we're going to define the hx to be the sum, to be the infinite sum of the gk prime x, just gx. Let's see, just the gx. G prime x. Okay, so actually one of the results we showed in the previous chapter is that if we have integrable functions like this, and the absolute value of the integrals, the sum of the integral of the absolute values is finite, then that means actually we can also show this pretty easily using the dominant convergence theorem to show that this integral of hx is also just the infinite sum. Okay, so that's pretty easy to show. Or you can just use the result before. I think I put the number of the theorem on the notes. You can refer back to the notes, then this will hold. Dx. Okay, so such h exists, and the integral of h is equal to that. Okay, and also the since each gk is in AC, we know the fundamental theorem calculus is true, so that means gkx is equal to gk. So now this we're going to use the special point c. That's equal to this plus c to integral of c to x g prime t dt. Okay, so we know that because g is absolutely continuous, so we know that. And then we take a partial sum for k from 1 to n, gkx. So that's what happens. Take the sum of the left-hand side is equal to take the sum of the right-hand side, 1 to n, and also plus the sum for k from 1 to n, cx gk prime t dt. Now, what we have in mind is that this one goes to the sum of this series, right? And when n goes to infinity. And also we know that this one will also go to, as n goes to infinity, it's just the infinite sum. But we know that this is true. So that means the infinite sum is just approaching to that. Okay, so it's approaching to this dx. So this is what happens on the right-hand side when we take n to infinity. And we know that they're all well defined. So it's not AB, but it's Cx. Okay, because h will be integrable. So the right-hand side, both of the terms on the right-hand side are well defined. They're finite. So that's why This is a well-defined. So this is just convert to the left-hand side, just convert to the sum of these two. So this is what we're going to define. This, let's say that the infinite sum is going to be defined as the gx. So the gx, which is defined as infinite sum of gk, will be just equal to the right-hand side, which is the limit of the right-hand side, which is this. Okay, so now remember that this is just a number. So let's see. This is just some number. This is the integral of indefinite integral of a integrable function h. So that means g is in AC, right? Because this can be written, the g can be written as this absolutely continuous function, and this is just a constant. So that's why this is in AC. And also the derivative of g will be equal to hx. But hx is known to be the sum of this, right? So that's why it's just the sum of gk prime x k from 1 to infinity. And that finishes the proof. Okay. Well, I just want to make two remarks. So there are two very short examples I provided in the notes. One example is that the composition of absolutely continuous functions may not be absolutely continuous. Okay, it's not like continuous functions. When we take a composition of continuous functions, we still get a continuous function. But if we take composition of absolute continuous functions, the result may not be absolutely continuous. And the example is that if we set f of y to be y cubic root of y, and then we set gx to be cx cube cosine pi over x cube, if x is between 0 and 1. If x is equal to 0, we set to 0. So both of them can be shown to be absolutely continuous. So this y is between -1 to 1. Okay, so we can easily show that both of these two functions are absolutely continuous. Actually, we can show that our Lipschitz continuous. Just take a derivative and see that the derivatives are bounded by some constant, so that means they're Lipschitz continuous. But the decomposition of these two on x is something we have seen before, because it's just the x cosine pi over x. But this function, we can choose a partition such that the variation over the partition is going to be is blowing up when we choose the partition right at the grid point, or right at the point where this is equal to +1, -1. So that means f composition of f and g is not does not have bounded variation. And if it's not doesn't have bounded variation, that means it's not in BV, that means it's not in AC. Okay, it's not absolute continuous either. So that's one example. So this is not in BV, and that also means that FG is not in AC. The second example is that when we have a sequence of absolute continuous functions and we take a uniform convergence, the result may not be absolute continuous. Okay, so the absolute continuous is not closed under uniform convergence. So this is again different from the continuity. If we know as some functions are, say, continuous over a closed interval, and in this case actually they are uniformly continuous, then we take a uniform convergence. If the functions are uniformly convergent, the limit function will be also uniformly continuous, but it's not true for absolute continuous functions. The example is this. So if we take fk to be 0 when x is between 0 and 1k, and we take a value, again the common example used, which is this. then we can show that fk is absolutely continuous for each k, because when the oscillation is too large, it becomes 0. Over this interval, it becomes 0. So over this area, it has a fixed oscillation. Okay, so it's in so this one is in AC, AB, 0, 1. But we can take the limit of fk. We can show that this fk actually converts to f, which is equal to x sine pi over x. Which goes to this f uniformly. But this function f, we know that is not in AC. Okay, so this is you can take this as a practice. Easy to show that the absolute continuity is not closed under the uniform convergence. Okay, so you do have a sequence of absolute continuous functions, and this sequence converts to some function uniformly, but this limit function is not absolutely continuous.